Hello, everyone. This is Radek, my colleague, and this is Kefu. We've been working on Crimson for more than 1 year, and we are working for Red Hat. It's very happy to have you guys join our session. In this session, we will update you guys with the progress of the Crimson recently, namely how we rebuilt a fast OSD using in the future.
But to understand the reason for starting the Crimson project, I believe it's quite important to give you some background about the reasons, about the changes in technology that made us to make the decision for doing Crimson. I believe that one of the most important one is actually improvement in speed of storage. When the initial implementation of Ceph OSD was written, it was targeting spinners. From a spinner you can get around 150 I/O operations per second. But after that, we saw a proliferation of solid-state drives. SSD internally is very well parallelizable. Combined with an interface, a connector interface, allowing you to leverage of this great level of internal parallelism, it can give you around 1/2 millions of IOPS, like in the case of recent NVMe-based SSDs. Is this a huge number? Well, I personally prefer to visualize that with another metric. Let's imagine you have a single CPU core clocked around 3 gigahertz. Quite standard thing. When you need to handle a spinner, your budget is around 20 millions of cycles per single operation. It's a lot. But when you are doing the same with NVMe, you get around 6,000 of cycles. 6,000. But, well, we are doing a network storage. So maybe we are luckily bottlenecked by our network interface card, by our NICs. Is that the case? Well, unfortunately, no. Unfortunately for us. Network speed improves as well. But what about our computational resources? What about CPU? The orange dataset is a visualization of a Moore law. The law brings two main benefits. Of course, it allows you to put more transistors on the same surface, on the same area. But there is a second benefit. It's due to the Dennard scaling, aka MOSFET scaling. Roughly, it says that when you shrink your transistor, its power density stays constant. So you are not only shrinking the area, you are also shrinking the need for power. You are freeing your power budget. The best idea for years to spend those extra savings were just to bump up the frequency of single core. It's quite a good idea because it allows you for vertical scaling. It disregards whether your workload is parallelizable or not. Unfortunately, something changed around 2005, 2006. The vendors, CPU vendors, hit the power wall. As a result, the frequency stopped growing. The Moore's law gives us only the reduction of size, only the ability to pack more things on the same area. And vendors use that, spend that extra budgets in two ways. First one was a try to exploit more instruction level parallelism. CPU cores got beefier, they are able to execute, they are more superscalar. They are able to execute more instructions in the same cycles. But another idea for spending the extra budget is just growing the number of cores we have in processor. It's clearly visible. It started growing very much, and we expect it will continue. But scaling your CPU horizontally puts some extra requirements on software. And is our current Ceph OSD incarnation ready for that? Well, Kefu will give you some introduction and will describe some problems we are experiencing right now.
Thank you. Before going to the pain point of OSD, I'd like to have a very quick recap of how the data flow looks like in existing OSD. As we know, Ceph pool could contain millions of the objects. Each of the objects has an object ID attached to it. And after we hash the object ID, we have a number, and we modulate it with the number of the PG assigned to the pool, where we have the PG number. And with the help of a crush algorithm, we can map a PG number to a couple of selected OSD. So the client is able to find the OSD which it should be talking to when sending a request. On the OC side, the messenger will be reading from the wire for the request. A request is consisting a set of operation which are targeting to the same object. After the messenger reads the request from the wire, it will enqueue the request in a shared queue, and then it will dispatch the request to the PG. But before the request reaches the PG, it needs to acquire PG log, which is represented using the trapezoid, the PG log, which is a grand log, because there's a lot of things going on in parallel. As we know that multiple clients could be accessing the same object at the same time. And we also have a lot of background tasks running in the background. For example, we could scrubbing a PG when a client is accessing that object. So we need to have a consistent view of a PG and the object. So we need to protect the status using the PG log. Unfortunately, this happens a lot in the PG, where we have three logs out there. Actually, there are more of them. So we are suffering from the PG log in the OSD. And after the request made its way to the underlying object store, it will need to acquire the queue But the queue, again, are protected by the different locks. So again, we are still suffering from the locks in the object store. This is a frame graph I collected when performing the write test with 4K using the RADOS bench write. As we can see, that there's a lot of time, a fair amount of time spent working on acquiring the lock and relinquishing the lock. Here, and here. And the same applies to the PG thread. And this is another evidence of the PG lock. This is a different one. Here, it's the message worker thread, which is responsible for talking to the kernel for grabbing the message from the wire and sending the message down to the wire. And it's still take a lot of time talking to the kernel for the traffic. Let's take a closer look at it. It's used a lot of time to call, send message, and receive message. This is a system call. So a natural idea is to remove the lock as a whole. So we stand up, look around. So we found we are not alone in this area. There's a lot of emerging technology and methodology to try to fix this problem by removing the locks and enforcing the share nothing model. C* is one of them. Another idea is to do the kernel bypassing, namely to use the user space driver to drive the network interface card or the underlying storage devices. DBDK and SDBK are two of them. And another idea is to avoid memory copy between user space and the kernel space. To verify our hypersource solution, we come up with a project named Crimson. Actually, this project started like 4 years ago, but the first line of code was submitted to our GitHub repo 1.5 years ago. The idea of Crimson is to rewrite the I/O path from ground up, from scratch, and to rethink the I/O path out of the box. The goal of Crimson is not port existing OSD to a new framework or library. It's try to use whatever we have to program to focus on the future. By future, I mean the future device and the future and the faster network interface card and the faster storage device. This is a reworked data flow of the Crimson OSD. As we can see, we actually transform the OSD into a single-threaded application. Each thread is represented in the blue area, and the messenger, the PG, and the object store are all living in a single thread and pinned onto this thread. And this thread is pinned to a hardware core, which implies that we will not have to, the thread will not have to competing with each other for the shared resource. So let's imagine if we have a box with 48 CPU cores, we are able to deploy 48 OSD on the same box with better performance. But future also implies a different thing here, because in the Asian world, when we are serving a request, we are blocked when reading the request, and we are blocked when we are writing response. And the POSIX thread is on hold, but this does not apply to the futurized world. I mean, we are using the C* to reprogram the Crimson OSD, where we're using future promise and deferred I/O, where the blocking call are not blocked anymore. when a core is blocked, the thread will be put, the physical thread will turn around to work on other tasks which are not blocked. Which we start from an oversimplified OSD to prove our hypothesis solution, which only supports a single replica, and currently it's only support memory-backed storage, and it only supports very basic I/O path, and it does not support the peering, but it will be around in 1 or 2 weeks. With this oversimplified OSD, we performed a lot of tests, and it proved very promising.
The results. For this particular stage of the Crimson project, we decided to use the performance of random reads. And let's start from the absolute number, of the total number we are getting from classical OSD and Crimson. Well, personally, I don't perceive this metric as very important. The main goal of the project is not to strictly deliver more IOPS. Its goal is to lower the computational cost of single IO. So let me treat this one just like an introduction to second and third. It's about, the important thing is about the computational resources, the cycles, the cores we used to deliver the numbers. In case of Crimson, is far lower, which is actually good. This allows us to, well, this can be visualized in a combined metric, which is just the number of cycles, CPU cycles we burn to deliver one IO. In Crimson, is almost 3 times better. But recently, we got also support for the write path. It's still basically in benchmarking, and on one hardware, we are beating the current OSD, even in total numbers. But, well, it's still not so important. The third graph is what we care the most. It's worth to say that the pre-prototype of the write path is, of course, is lacking, for instance, a support for PG lock. It's very simple. But on the other hand, on one of our machines, at inserta 07, we are seeing a lot of likely memcopy induced page faults when kernel wants to zeroize the pages we are writing to. And still, even with this extra cost, we are seeing reduction of computational costs. By the way, the fourth graph is just a bonus. It shows the instructions, the IPC, instructions per cycle. The higher, the better. We need to, of course, make some further steps. Basically, Crimson is at the moment an R&D project. We used it to very preliminary testing. Kefu will say more about our future goals.
Currently, the prototyping is in good shape. It's slim and it's fast, but we need to keep an eye on its shape. Recently, we observed a regression we didn't notice, and it's slimming to our branch, and it hurts the performance. We don't need to prevent it from happening again. So we do think that Our most important thing is to integrate the performance test into our CI integration. Namely, we will have a set of benchmark tests. Will be run whenever a pull request is submitted. And if the performance, if it hurts the performance, our CI, our Jenkins slave will vote down that PR. And we will take a closer look at it. And the second thing is to support RBD. Namely, it will require us to add a set of critical features. For example, we will need to support blue store instead of memory-backed store. And the second thing is to support peering and recovery. And in long run, we will come up with a fully futurized store instead of using the existing blue store. But before we are there, we need to support SBDK, add support of SBK to C star. After that, we will be able to talk to the underlying NVMe drive using C star framework. Before we conclude this session, I'd like to introduce guys some more information of this project. Since last year, we have like 123 PR submit to with the Crimson label on it, but the number is still counting, and we have 7 developers from Red Hat and Intel devoting their resource and energy into this project, and this project is still under heavy development. We have a weekly standard meeting discussing the state of the project, and the meeting is filmed, and the recording is available as a playlist in the Ceph channel on YouTube. And we also have the project Kanban on GitHub. You can always check it out to find out what we have accomplished, what we are working on, and what we will be working on. And we always welcome new joiners. Even you are just interested in this project, we are available on the Ceph Dev mailing list and the IRC channel. So any questions, problem? Okay. I didn't expect this.
How are you going to deal with RocksDB? How to integrate it into Crimson, or maybe replace with some other DB, whatever?
So the question is how would we plan to integrate Crimson integrate the RocksDB and other DB-KV backend into Crimson? That's a good question, actually. That's something we are thinking about. In short term, we have 2 approaches. One is we add a set of call named alien call, so a C star thread can post message to a traditional thread by passing message and waiting on it. We have a wrapper on it, so the particular thread can talk to Crimson thread. But that's the bottom line. We name it alien call. So the Blue Store or RocksDB will live in an alien world where it can always need to do the cross-call communication between C star. And another way to do it is to extend the RocksDB so it's able to use C star thread. Namely, we will need to use user-space scheduler like uContext to do the context switch in the user space to pretend to be a blocking call. That would be involving but a more difficult approach. But performance-wise, it would be more promising, I guess.
But in very, very long term, there is also a third possibility. Maybe we won't want to use RocksDB at all. The new inventions in storage hardware gives us some reason to consider doing that. I mean, especially persistent storage that is as fast as RAM. This could kill the need for instance, for journaling, for WAL.
What network stack are you using with C star, the socket interface or DPDK? What network stack are you using with C star? Is it the socket interface or DPDK?
The question was about which exact network stack we are using here. Well, it was the kernel-based one. We haven't used DPDK-based one yet. Any other question? Okay.